Chapter 1 of physics is going to discuss space, time, and mass. And in introductory physics, our real goal is to study how things move. We're going to study movement in this first semester a whole lot. And to study movement, we need to first establish what kind of world we're working in. And we're working in intro physics in the ideal world. And in the ideal world, we can describe particles, we can describe things moving, and we can describe them as little tiny dots. These little tiny dots we will call ideal, as your ideal particles. This is what your book refers to them as. You might also hear these referred to as point particles. It's the more common name for them, a point particle. So this is trying to describe objects and how they move in the ideal world of physics. And we just use these ideal point particles. What is an ideal point particle? It has certain characteristics. It has mass, but despite having a mass, it has no size. Mass, but no size. So it has mass, we can find it, we can find where its position is. The second thing we want to know, position. But we need to make note that this particle, despite having a position, it has no size. It's infinitely small. And finally, we don't want to know just position any old time. We need to know its position at all times. So we combine these two to really tell us position at any time. Okay. Now this is something you should be familiar with from your calculus class. You should have been writing equations to describe functions. And in physics, we're going to do the same thing, except we're going to describe positions, usually with a little x variable, where something is in an x position, and we'll go over what that means in a minute, as a function of time. So we have dependent and independent variables. So time would be independent and x would be dependent variable. So maybe we have some kind of equation. X of t is 2 times t. And that describes where a particle is as a function of time. But we'll get into those details a little bit later on. So mass is something we can measure. Size we don't have to worry about because ideal point particles have no size. So let's go on to the second one. The second guy is position. How do we describe position? Describing where something is. Well, to describe a position, where something is, how something's moving, where it's going, we kind of need a couple different things. We need a starting point. Also known as an origin, where we're going to begin. We need an endpoint. And we kind of need a map so that we know the route that we can take. So if I ask the specific question, how do I get from Arlington to Georgetown? Okay, Marymount University, we're sitting right here in Arlington. To get to Georgetown, we'd probably the easiest route, maybe we'd cut through Roslyn, go across the Key Bridge, and then we're in Georgetown, right? And then we can establish what our origin is. Our starting point is Arlington, and our ending point is Georgetown. So we can bring up a map. We can bring up a map that shows us this, and let's see what we got. Okay, so we got our map. We have our starting point. We're starting right here in Arlington. Let's make that come out a little bit better. Here we are in Arlington, and we're just going to go straight down this road to get to Georgetown. Now, does this look right? Does this look like what anybody expected? Well, for those of us familiar with the DC area, this is the entirely wrong map. Why is this the wrong map? What went on? What's wrong? I know how to get from Arlington to Georgetown. I've done it before. It's on my bike ride home. So why doesn't this map doesn't match what I expect it to? Well, I can look closer. I can see Fort Worth. Is there a Fort Worth anywhere near Washington? No. Fort Worth is actually in Texas. So this map is actually a map of Texas. There's an Arlington in Texas, and there's a Georgetown in Texas. So this is a Texas reference map. We can get a different we expect. This different map has, I would expect to see Arlington, the map that I'm used to taking, and I cut through Arlington. I'm going to go through Roslyn. I'm going to come around. I'm going to go over my key bridge, and I'm going to end up in Georgetown where I expect. So this is the map that I expected to see, the one that I described. This map is for Virginia. Again, this is what I would expect to have. The difference between these two maps, called a frame of reference. And these frame of references, they depend on the specific coordinates that you're going to use to describe where something is. So they depend on something called a coordinate system. So frames of reference and coordinate systems are intricately related. They play off of each other. Usually in physics, in this class, we're going to use something called a rectangular coordinate system. This is where we describe where something is in kind of a rectangular grid. So we describe it based on where it is in some x position, some y position, and maybe if we need to, some z position. So let's look at our maps. Let's see. Here we are in Texas. Here's our Texas map. I'm going to start by drawing a coordinate system. Let me draw a coordinate system. I'm going to start it at my origin. Start it in Arlington. Okay. And what I've drawn here is an x-axis, and I have a y-axis. Now you notice I don't really need a z-axis. I'm not coming up out of the page or anything. I'm on the flat ground. I drive in 2 dimensions. So what we can see from this this map, this coordinate system that I've drawn in this particular reference frame to get to Georgetown, I really kind of can almost get away with only one coordinate. What coordinate can I get away with going mostly in? I can pretty much drive almost directly south, almost entirely in the y direction, and end up at my goal destination. So for this map, this particular coordinate grid, this particular reference frame, I'm really mainly only moving in the y direction. So this is kind of like a one-dimensional coordinate system. I'm really only moving up and down. Only really have to travel in the y direction. This is contrary to when I go to Virginia, then our Texas reference frame. We can look at our Texas reference frame and see that our Texas reference frame has a completely different time. Texas reference frame. What kind of time do they have in the Texas frame? They have central time. As opposed to my Virginia map, let me draw my coordinate system. I'm going to start my origin right here at Arlington. This is my starting position. Okay. And I can extend this out as far as I want. So there I am in my x-axis. Here I am in my y-axis. And what we'll notice here is I got to follow these roads more or less, but I'm moving in both the x and the y directions. I'm moving kind of diagonal. So I have to move a little bit in the x direction, and I have to move a little bit in the y direction. So I have two different directions I'm going in. So this is kind of a two-dimensional coordinate grid. So I need to describe this reference frame, this trip, in the x and the y directions. Now I'm driving or riding my bike these places. There's a guy that sometimes, actually often, needs to travel in three different dimensions. He needs to travel in x, y, and z. If I'm going to try to show that on this map, it's very, very hard to do because it's a two-dimensional plane. But if we can imagine going to this place, let's go to the White House. President, he doesn't just drive around. It's kind of dangerous for him to drive around. So he's got a little helicopter pad, and he's going to take off, and he's going to launch and fly up into the air. So he's flying up into the z direction. Can't really show that very well here. But he's going to fly up into the sky. That's going to be the z direction. So he would travel in the x direction, the y plane, and the z plane, since he's in his helicopter traveling up into the air as well. So we have all these different coordinate systems. If we take each coordinate system and all the points in our coordinate system have the same times, literal times like a clock, then this is what we call a reference frame. So we have two different reference frames. We have our Virginia reference frame. Every single point in this coordinate grid, every single point on this map has the same time on it. So it's all the same frame of reference. That's all a reference frame is. A coordinate system where every point has the same time. Every point has the same clock. So this Virginia reference frame is different, where we have Eastern time. So those are coordinate grids and reference frames. So let's remember that our goal here is to study, really we're trying to study motion. And we can study motion with some base quantities. We study how things move, how particles move, how point particles move, using these three quantities of mass, how much mass something has. Remember, our ideal point particle has no size. Its position, where something is. So we need a coordinate system, we need an origin, we need to know where we're starting and where we're finishing. We need to know if we're in Virginia or Texas, for example, so that we can establish that everything is in the right times. So we know how particles are moving as a function of time. So again, this combination of position and time gives us our coordinate grid and our reference frame. Our coordinates and our reference frame. Okay, but how do we measure these? How do we make measurements? That's, after all, what we're going to do in physics. We're going to go into the lab and we're going to measure things. Well, we measure things, and when we measure them in units. And in this course, we're going to be using the System International, the SI system, the established scientific consensus units for measuring. For measuring mass, we have specific units. And any time I'm discussing measuring units, I'm going to put quantities into brackets. So what that means, what do I mean by that? I have this square bracket with an m inside of it. That means that I'm going to describe the units of mass. The units of mass, the standard SI units of mass, are going to be the kilogram, kgs. Standard SI unit of position, and in this case, I'm going to use x, where something is on some x-axis. So we saw our coordinate grids, we saw x position is usually horizontal, so I'm going to say x for position for now, and we usually measure position, where something is, in units of meters. Position is after all kind of measuring a length, and we use meter sticks to measure length. And finally, we have an SI unit of time, how long something takes. We're going to use the SI system, this Instrument International again, and that SI unit of time is going to be the second. We measure all these units, kilograms, meters, and seconds. What you want to do is you want to study table 1.2, which gives you prefixes. You want to study table 1.6, which gives you time conversions, and try to understand checkup 1.2 and 1.3, which will really help to solidify these different units and how to convert between them. So let's look at these base units a little closer. Base units are meters, seconds, and kilograms. We can combine them to get interesting things, and that's what we're going to be doing a lot of in physics. So something like an area. We should be familiar with areas. Let me think about a box. Think about a box. If I want to know the area of this box, then I take its length and I take its width, and I multiply them together. So the units of area, remember something in brackets means I'm asking about units, it's going to be the units of length times the units of width. Well, how do we measure lengths? We measure lengths with meters. So the units of area have to be equal to the units of length, which are meters, times the units of width, which are meters, to give us the units of area are meters squared. We can look at other quantities. We can look at something like a volume. A volume. So this is a box that has a length and a width, but it also has a height. So I'm going to draw my 3D box. I have a length, I have a width, but I also have a height. So my units of volume, again, the square bracket means units of volume, are going to be equal to the units of length times the units of width times the units of height. And I can just plug in all my units like this is some kind of regular algebraic equation, because that's all it is. I'm just working with letters instead of numbers. So I have units of length are meters, units of width are meters, units of height are meters. So I end up with meters cubed. Units of volume are cubic meters. I can look at other values. I can look at other quantities. Something like density. Density is a mass divided by a volume. So if I want to know the units of density, then I'm going to take the units of mass divided by the units of volume, and the units of mass in the SI system, if you remember, are kilograms. Units of volume, we just figured out what those were, are cubic meters. So the units of density are kilograms per meter cubed. We're going to jump ahead a little bit to a later chapter, and we're going to talk about something called V. V we'll talk about as velocity. We'll get more detail this later. A velocity is a change in position, so it's a length divided by a change in time. How do we measure lengths to get the units of velocity? Well, we know that the units of velocity are going to be the units of a change of position, which is just a length, divided by a change in time. The units of a change in position are going to be meters. Units of a change in time are going to be seconds. So we get meters per second. This value V, again, is for a velocity, which kind of tells you how fast something is going. We'll talk about that a little bit later at the end of this chapter. To study this a little bit better, to get some practice with it, I suggest you try checkup number 1.5. It's a pretty good practice. Moving forward, what you want to do is you want to read sections on scientific notation, trigonometry. Don't skip this trigonometry section. It's in its own separate little box. When I was in school, I would usually skip those little separate boxes, but this trigonometry one is very important. You don't want to skip that. You want to read about dimensional analysis, conversion factors, and sig figs. If you don't understand these sections, if you don't understand this material, this is the point where you send questions This is the material that I think is a little difficult, a little tricky. I'm going to go over some of it now, but if you don't understand these parts, send me questions and I can answer them. I can cover it, I can help you out a little bit. So, what are all these things? Scientific notation. Well, this is basically just writing a number as a factor of 10. So I have the number 100. I want to put that in scientific notation. So I want to write that as a factor of 10. 100 equals 1 times 10 to the 2, which is 1 times 100. Okay, so I'm kind of breaking numbers down so that I can have a simplified way to express something. I can have 3.14 times 10 to the 3. So I can expand this out. 3.14 times 10 to the third. That's 10 times 10 times 10. It's going to be 1,000. So that's going to be 3140. And what we can do is we can compare what the numbers look like. If I have the number normally 3,140, I can write it in scientific notation so that I have one number followed by a decimal multiplied by a factor of 10. It's just a shorthand, very useful for scientific notation, particularly when we get to the concept of significant figures, which will be very important for both the problems and the lab portion of physics. Moving on to the next important section. So with trigonometry, what we want to keep in mind, and we will use trigonometry a lot, so this is very important to understand. I can't emphasize this enough. We want to get really, really good with this shape right here. This is something called a right triangle. It's called a right triangle because it has a right angle, a 90-degree angle, and we have some angle that we can draw in here. And we have a side that's really close, really adjacent to this angle. We call this the adjacent side. We have another side that's opposite, so if I go opposite to my angle, I have my opposite side. And then we have the final side, the third side, the big long side. We're going to call that the hypotenuse. Okay, we have some trig functions we can write for these things. We can write sine theta. That's going to be equal to the opposite side over the hypotenuse. We have cosine theta. Cosine theta is equal to the adjacent side over the hypotenuse. And finally, we have tangent of theta. Tangent of theta is going to be equal to the opposite side over the adjacent side. What are the units that we have here? The units of the sine of an angle are going to be the units of the opposite side over the units of the hypotenuse. How do I measure the length of a side of a triangle? How would I do that in the SI system? I'm measuring a length, so the units would be meters. So sine of theta, the units of sine of theta, are equal to meters divided by meters. What happens when a meter is divided by a meter? Meter cancels with the meter, and we end up with just 1. This is a special quantity, something called unitless. The sine of an angle has no units. And this is what we expect. We know from math that the sine of an angle should not have any units associated with it. So we performed a method, an approach, something called dimensional analysis. We looked at the different dimensions that we had, the different units, and we saw if they made sense with the answer that we expected. From the math, we expect that the sine doesn't have any units, and sure enough, that's what falls out. And it will fall out with the cosine of the angle and with the tangent of the angle. Now the final point to discuss is something called conversion factors. So Americans, we're really stubborn and we hate the metric system, so we don't really use it. Proof that Americans are stubborn? Speed limits. If you're driving down the road and you see a speed limit sign, what is it usually measured at? Something like maybe 60 miles per hour. 60 miles per hour. That's 60 miles per hour. Well, you can write this as a fraction. miles per hour. Per is a fraction. So we have 60 miles. So that's some distance that we're traveling in some amount of time in 1 hour. Well, if we remember, that's a distance. That's a change in position, change in x. And that's over some certain time, over 1 hour. So that's a change in time. So what is this? Change in x over change in t. That's a velocity. If we think back to a couple slides ago, we were talking about different quantities we can do, combining units. We had something called velocity. The units of velocity were the units of change in x over the units of change in time. But in an SI system, that's meters per second. Meters per second are not equal to miles per hour. Or are they? They're both valid velocity units. A velocity is equal to a distance over a time. Both these units are giving you a distance divided by a time. So you can use either of them. They're equally valid. What's not valid is saying that they're exactly the same. You need to convert between the two. So there's a conversion factor. There's conversions that need to go on here. You can see these conversions in your book, and I'll do a quick example using the factor label method. So I have something, we're going to say 60 miles in 1 hour. That's how fast I go in a given amount of time. I want to get this into meters per second. So I'm going to use something called a factor label. I'm going to figure out, I'm getting rid of miles. So I'm going to put miles down here on the bottom of our fraction, and I want it to be in meters. So I'm going to put meters up here at the top. I can use a table from my book, table 1.4, to figure out that there are 1,609 meters in 1 mile. Then if I look at what I'm doing here, I'm going to multiply all these things together, and my miles are going to cancel out with my miles. A mile divided by miles gets rid of those units. So I'm going to end up with just meters. So that will give me meters per hour. I want meters per second. So now I need to get rid of the hours. So I put 1 hour up top. That will do what I want. I want to cancel out my hours. The hour in the numerator cancels with the hour in the denominator. And I want to get it into seconds. So I need to know how many seconds are in 1 hour. That's going to be 3,600 seconds. I can either memorize that, or I can use table 1.6 in your book. Alternatively, you could also use the grand and powerful Google. Give you these same conversion factors. So I'm going to multiply all these things together. My hours are going to cancel with my hours. My miles are going to cancel with my miles. I do this multiplication out, and I get 26.8 meters per second. So 60 miles per hour is equal to 26.8 meters per second. And if you do this, if you turn this in, if you turn this in on an exam, you get a big fat X. That is completely wrong because of something called sig figs. We need to compare the number of significant figures we have in each of these numbers. Now I've boiled it down really to 4 rules of sig figs. The 4 rules are as follows. Anything that's not a 0 is significant. Any non-zeros are significant. 1, 2, 3, 4, 5, 6, 7, 8, 9. Anything that's not a 0 is significant. Any zeros that come between any 2 non-zeros are significant. If I have a number 101, my 1 is significant because it's non-zero. My 1 is significant because it's non-zero. My 0, this is a 0, but it's between 2 non-zeros, between these 2 ones. It's significant. So in this number 101, I have 3 significant figures. Okay. If I have zeros that are to the right, also the way I think of it is behind a decimal place, and they occur at the end of a number, then they're significant. What that means, let's say I have a number like 1.2, 2560. Well, I look at this, these numbers. I know 1 is significant, 2 is significant, 5 is significant, 6 is significant, because they're all non-zeros. So according to this first rule, I have 4 sig figs. I look at this zeros. This 0, is that 0 between two non-zero numbers? No, so it's not significant according to rule number 2. I look at rule number 3. 0 to the right or behind the decimal place. So am I to the right? Yep, I'm to the right of the decimal place. Okay, so the second thing I have to do, and I have to be at the end of a number. Am I at the end of a number? Yep, I'm at the end of a number. Check. I have 1, 2, 3, 4, 5. I have 5 sig figs in this number, according to rule number 3. Finally, I have zeros. Rule number 4, zeros to the left of decimal and in a number greater than 10 are significant. So if I have a number like 20.0, how many numbers are significant? Well, 2 significant, yep, because it's non-zero. Look at my second number, my second 0. Zeros between non-zeros are significant. Is this 0 between two non-zeros? No, so it doesn't satisfy rule number 2. Number 3, zeros to the right. Is this number to the right of my decimal? No, it's not, so it doesn't satisfy rule number 3. Look at rule number 4. Zeros to the left. So that's what I'm talking about. I'm to the left of the decimal place and in a number greater than 10. 20 is greater than 10, so this 0 is significant. And then finally go to my last 0. 0 is to the right of my decimal and at the end, so this number has 3 sig figs. Okay, so those are just a few little, those are the rules and a few little examples. So let's look at the actual situation that we have. So we have this number and we want to know if it's significant. We want to know how many sig figs we actually have to leave. The important thing is that when you're doing a problem, the answer to your problem adopts the lowest sig fig. Lowest sig fig. So what we're trying to do is see what the equivalent of 60 miles per hour is in meters per second. 60 miles per hour is equal to, well, we got 26.8 meters per second. Now I need to analyze my sig figs. If I look at 60 miles per hour, I see one non-zero digit. My other 0 is not significant because there's no decimal place. So that's going to be 1 sig fig. My answer, I see 3 non-zero digits. So that's going to be 3 sig figs. I want to adopt the lowest number of sig figs in my answer, the lowest sig figs, so I need one significant figure. So I do 60 miles per hour, and I do some rounding, and I round this. 26.8 becomes 27 meters per second, and that's my answer. Again, nope, big fat wrong answer. Why? Because this has 2 sig figs. I need to have just one significant figure. So I round it again. 60 miles per hour is going to be equal to 30 meters per second. If I'm being strict with my sig figs, then this is going to be my final answer. Again, because I need to keep the same number of sig figs. 1 sig fig here is 1 sig fig here. And that is the end of chapter 1.